Alright guys, welcome to week 2 of IS50B. We are live here on OBS, which is not the same thing as IBS. IBS is irritable bowel syndrome. Ada, do you know what irritable bowel syndrome is? No? Good. Okay, so here we got the band from Twitch, PogChamp, rendered in 24-bit color inside of Putty, inside of a text-based interface. I made a tool called Asaidi that can render 24-bit color images inside of a terminal just for fun because it amuses me. But we might use it this semester to do cool stuff. So let's go and take a look at some of your projects. So who got the Veroni thing working? McLaughlin. Okay. CD Veroni. Okay. Nice. Do you want to do Veroni relaxation? Sure.
Why are there giant sketches of colors?
It's like a random map generator, Ada. So what it's doing, it is randomly making a map, and
That does not look like a map.
it doesn't look like a map.
I mean, in Mario Odyssey, purple is for poison. There's two different shades. I think this kills you, maybe, and this kills you, but the one that the promise plant spit out, you only lose a heart.
Okay. All right. Okay. We got to make Doom or Wolfenstein. That's what I was thinking. Yeah. There's a couple things I want to do in this class, and one of them is to teach you guys the basics of 3D rendering and actually make a 3D renderer. And we could do it inside of Putty, which would be hilarious to have a Doom running essentially inside of a console, inside of a text-based console.
Thank you.
Which would be amazing. And also, I was thinking about doing like a real-time strategy game. So there's mouse support, by the way. So you can make it so you can click on things, and so you could click on a troop and then move it over here. And I was thinking about doing that as well, which would be highly, highly amusing to me. So, yeah, Muya was the one who told me about mouse support. I didn't know that existed until he told me about it. So, it's in the read library, I believe. Oh no, it's in colors. It's in colors. So if you CD colors. Colors demo. That one? Right. So you can click and it'll read the mouse location. And you can hit keys on the keyboard and you can see the ASCII, they're not exactly ASCII codes, but the numbers of the things you're typing come out as you type immediately. You don't have to, it's not in cooked mode. Normally when you enter things, you can't read anything until enter is hit, but through the read library, you can run stuff and have it like page up, page down, home, end, insert, delete, backspace, A, B, C, capital A, capital B, capital C. You notice how these things are ASCII codes? So it's the ASCII codes plus a bunch of other numbers that represent the different keys on the keyboard. F1, F2, F3.
What are you teaching right now?
I'm teaching my second semester game development class. So,
But what are you trying to show them? We're trying to teach them.
I'm showing them that you can hit keys on the keyboard and then just have numbers immediately appear. Of course, this is what key was hit, essentially. So, so let's talk about stuff. We were working on this last time, right? Linear. Okay. So let's see if we can figure out how to do a convex hole today. So what is a convex hole? Let's pull up a, let's do OneNote maybe.
Looks like your game that you made. That looks like your game that you made.
That is the symbol of the game that I made. One of those Discord servers is for custom TF, the other one's for all Quake World.
Not all Quake.
People have made other mods for Quake World other than mine. So this is 1.22.21. Okay, so let's talk about convex holes. This is actually really useful, and it's used in Quake, for example, the Quake engine uses these things. So what is a convex hull? What is a convex hull? So let's say you've got a bunch of points. There we go. You've got a point here, a point here, point here, point here, point here, point here, point here, point here. You could, like, if you wanted to outline this object, you could do something like this, right? And draw a line.
Connect the dots.
Connect the dots, right? I don't know. Make another point there. But a convex hull is one that has no angles, kind of like this. Instead, a convex hull is, you can think of it as like a rubber band that extends around all the points. So a convex hull says that if you draw a line like that, all of the points are to the right of it. Okay, and so if the line included this guy here, this would not be part of the convex hull, because if you drew this plane here, some of the points sure are going to be on the line or to the right, but some of them would be to the left, and so that would not be allowed. Okay, so a convex hull is a way of wrapping points in a you can think of it as like a rubber band, you know, and you just put the rubber, like if those are nails on a board and you had a rubber band, you released it, the rubber band would snap down to the outer nails and ignore the inner nails. And one nice thing you can do about that is you can delete these inner points too, as well. And so a convex hull would be this. Okay.
Looks like a smiley face for you.
Right.
For
and so if you have this vector here as one part of the whole, everybody is to the right. And for this line here, you see everybody's to the right. And for this line here, everybody's to the right. For this line here, everybody's to the right. For this line here, everybody's to the right. For this line here, these are infinite lines, right? Everybody's to the right. And so these lines together form the convex hull, right? Or technically the line segments. Okay. So if I make this in galaxy pen, this becomes the convex hull. And so that's going to be your next homework assignment. Is doing that. Is that galaxy, or maybe is that glitter?
I think that's rainbow.
Is that rainbow?
Yeah, I think that's
Oh,
rainbow.
you're right. You're absolutely right. Oh, thank you. There we go. There's the galaxy pen. All right. So your assignment is going to be to take in a bunch of points and return the convex hull. Okay.
Pentagon.
And there are some very, very neat algorithms for doing that. All right. So you find the outermost points before drawing those secant lines. So there's at least 4 different ways I know of determining the convex hull of a bunch of points. You can brute force it, and so brute forcing it might be where you might want to start. Do you guys remember how to tell if something is to the right or to the left of a line? This is why I introduced this last week when we were talking about the toolkit of options for doing linear algebra. Do you guys remember what function you can use that will tell you if a point is to the right or to the left of another point?
Dot product or cross product?
Which one, Nita? Is it dot product or cross product?
No, I'm reading.
I know. Okay, so we've got dot product, we've got cross product out there. Let's review. Okay, so dot product, if you have 2 vectors pointed the same way, it returns 1. If you have them pointed in opposite directions, it returns -1. And if you have them at right angles, so right angles to each other, it returns 0. Okay. Dot product does not distinguish between right and left. So if you are pointed completely to the left, it returns 0. If you're pointed completely to the right, it returns 0. So dot product cannot be used to determine. I hesitate to say cannot, but yeah, you don't use dot product to determine if they are pointed to the right or left of each other. So what you want to do is cross product, right? So if you have cross product, that
Is today the
will return.
21st? Today's 21st.
I don't remember. It's either -1 and 1 or 1 or -1, whichever one. So if they're pointed forward or backwards from each other, it's going to be 0. If it's pointed right, it'll be 1 or -1. I don't remember which one. And left is -1 or 1, whichever one. It doesn't matter. And so this will tell you if all points to the right if it is 1, I don't remember, again, which one it is, will be positive, and all points to the left would be negative, or the other way around. Again, I don't remember which one it is. Doesn't really matter. Okay. So the answer is cross product. And so what you're going to do is, given a set of points, I guess I could just look it up because I wrote it down, right? It's negative to the right. Okay, sorry about that. So the answer will be positive, positive, positive 1 if it's pointed to the left, and it'll be negative 1 to the right. All points to the right, all points over here, all are negative. And all these points over here, all are positive. Okay. And so the rule for a convex hull is given a line, it is part of the convex hull if all points are to the right or on it. Okay. So all you do is the brute force approach. You would take 2 points, every 2 points basically, and then see if all the remaining points are to the right. And if it is, you're like, cool, you're part of the convex hull. Okay. If Cyberpunk 1.1 doesn't come out today, CD Projekt will have broken another promise. I've already uninstalled Cyberpunk 2077. Okay, so let's see. What's the application of convex hulls? There's a lot. There's like linear algebra applications, like if you're combining vectors of different kinds, find the area that is possible to be reached by the different vectors. In this case, you could actually just eliminate, like these points in the middle here, they don't do anything for you, right? So you can eliminate them. And just all you have to hold is the outer surface. So if you have a lot of dots, right? If you have a lot of dots that kind of define a point cloud, if all you have is the outer part, then you can get rid of all of that stuff on the inside and just come up with a polygon that kind of covers that area. And so if you want to see if something is inside, that's another thing that's really easy to do. You have a polygon that's a convex hull. You know, you got a convex hull polygon. If you want to see if a point is inside of it, you just simply cross product that point with all of the segments of the hull. If all of them say it's to the right, congratulations, that point is inside of the hull. Does that make sense, Mulia? So if it's a way of testing to see this point here is outside, this point here is inside. And so that allows you to create solid objects, right? So if you're trying to teleport to a spot, you can see if it's inside of an object or not. And this is useful, like I said, the Quake engine uses convex hulls for creating 3D things you can stand on and stuff like that. So if you want to see if a point is solid, you know, or open space, there you go. UE buttons could use this too, right? Yeah. Usually you use rectangles, which are, rectangles are really easy to test the inside of, right? If you have a rectangle, it's like, is it to the right? Is it to the left? Is it below? And is it above? Right? Is it greater than x1, lower than x2, greater than y1, lower than y2? Congratulations, it's inside of a rectangle. That's why we use rectangles a lot for things. The two easiest things to see if you're inside of are rectangles and circles, right? So, so for a rectangle, you just say, is it greater, if this is x1, this is x2, and this is y1, and this is y2. Remember, the y coordinates start at 0, 0 in the top left corner of the screen. So y goes down that way, x goes to the right that way. So if it's greater than y1 and smaller than y2 and greater than x1 and smaller than x2, congratulations, that point is inside of the rectangle. If any of those are false, then it is not within the rectangle. And so it's a very simple way of testing to see if you are in. And these things come up all the time in video games. Is one thing inside of another thing, right? Circle, circle. Are these two circles touching? I apologize to my grandfather. I apologize. My grandfather was an architect, and he could freehand a perfect circle. I can't. I cannot. He would just go like bloop. Yeah, see, no. Just bloop, perfect circle. I spent one summer day. He was like, just learn to draw a straight line first. I'm like, is that good? He's like, no. Yeah, you have to go.
There's a straight line.
You have to go back and forth. You have to go back and forth and make a straight line. I'm like, no.
This is a straight line, right?
That is a straight line. Yeah. Yeah. He gave up on me being an architect. He bought me like a drafting table in 8th grade and got me a square rule, and I took a drafting class, and no. No, sorry. So anyway, so if you have one circle, a circle is a center point, x and y, and the radius, right? So there are three things that make up a rectangle. There's the center point, a circle. There are three things that make up a circle: the center point and a radius. There's four things that make up a rectangle. You have, eight. Yeah, well, it depends how you do it. But like minimum x, minimum y, maximum y. So you have four integers that define a rectangle. You have three integers or floats or doubles if you're using that. Three numbers define a circle. Four numbers define a rectangle. So they're pretty easy to define. And if you want to see if something is inside of it or intersecting it, then that's pretty easy. You take the hypot, right? So if you have a point here, it's called x2, y2, and we'll call this one x1, y1. What you do is you just take the Pythagorean Theorem, right? x1 minus x2 squared plus y1 minus y2 squared. And if this number, this is the distance, this is the length, also known as the distance, right, between 2 points. This will come up all the time in this class, right? So that function is available in C++, and it is called hypot. And so you just pass in x1 minus x2, and you pass in y1 minus y2, and it will give you the distance. And so this is the distance, we'll call it h. And so if h is less than r, the radius, congratulations, you're within the circle. If x is or less than or, I mean, I guess you can choose whether or not the surface of the circle is in the circle. Yeah, so maybe you have x is less than r, you have h is equal to r, or you have h is greater than r. And this you have to be cautious about. Why do you guys need to be cautious when doing equals comparisons with floating point numbers? Why is that considered risky? Anyone know? Right, so you're gonna get a point. The point might be inside the circle. The point might be. Whoop! I just erased it. Let me go back to the pen that I was on. Pen that I was on. There we go. So the point might be inside the circle, might be on the circle, or it might be outside the circle. Right. So you got three cases here. But why is this one dangerous? Why is it dangerous? Because floats are awful because of rounding. Yeah. So floats inherently have error in them, and you can actually do the same computation, algebraically the same computation. But if you do it in different orders, or if you do it in different ways, you can end up with a different number. And so if you use double equals, a lot of times it'll work, and you'll feel confident. Look, it is successfully detecting when a point is on the radius of the circle, and then it won't. And that's really, really dangerous. And all sorts of problems can come out. Like, what if these points here are really far away from the origin of the world? What if this number here is like 5 times 10 to the 60th power, right? What happens is you start losing precision. So as you get further and further away from the origin of the world might be way over here somewhere, these numbers start losing precision. Right? Minecraft had this problem. The further you got away from the origin of the world in Minecraft, the more error-prone everything was. Right? So rounding, yeah, it's a tricky problem, and rounding is just the bane of you know, anybody who works with numerical data, really. The far lands, yeah. So basically, always, anytime you find yourself writing double equals with a double or a float, don't. Or just have that. No, just don't. I would just say don't. Just don't do it. I would use less than or equals or greater than or equals. And if you have to absolutely detect if you're on a line, remember a line has like 0 length, right? So, or 0 width, I should say. So, what does it really mean to be on a line that has 0 width anyway? And so what you want to do is you want to create a near function, right? And the near function will take in, you know, x and y and return true. It'll return true if x minus y is less than some epsilon, right? So you have to subtract x and y from each other, and if that's close to 0, then you return true. Okay, and so you might use 0.01. You know, or you might even pass in e as the parameter to near. So you could say if x and y are within 0.1 of each other, if they're within 0.01 of each other, if they're within 0.0001 of each other, return true. They're the same thing. And so what that does effectively is it gives width to your circle, right? It makes your circle's line a little thick, you know, a little thick, and so it'll pick up points in that width. Whatever you pass in for epsilon is essentially going to be the width of the line of the circle, and that's if it actually matters to you that if something is exactly on the boundary of a circle, you need to use that. You need to define how wide do I want the line of my circle to be. It is safer if you cast it to an int, not if you if the circle has a radius of like 5.4 and you want it to be on the radius, if it's 5.39 to 5.41, casting it to an int, you know, doesn't really help, right? Because it just becomes 5. And so having some thing like this is like good practice. Never use equality. Never use equality with doubles or floats. Always define a range of values they can be in, and then you just play with it. You just play with that error value and see, is it working? But that's why people prefer ints, right? People prefer working with ints because with ints it's precise. There's no an error in ints. Unless you get hit by like a cosmic ray or something. A cosmic ray comes in and flips a bit. Okay, so do you guys understand the code to find if you're within a circle, if your code to find if you're within a rectangle? Those are two very common operations. So we will need to generate a circle from the lines. You could, and you will. So this, though, the convex hull is a more precise. Like let's say you want to see if say you've got a person, right? A side view of a person looks kind of like this, right? They got a body, you know. A lot of times they'll use what's called a capsule. A capsule is a cylinder kind of looking thing. But let's just say that we're going to represent this person using a sphere, right? If you ever seen the Vitruvian Man, you know, the width of a person's arms are basically the same as their height, right? So if you use a sphere to represent a person, then you can test to see, let's say you stab, you know, or let's say you just, you know, you shoot a bullet and you want to see if the bullet's currently here. It's actually a projectile. It's flying through the world. You know, you shot a dart at somebody, let's say, and you want to see, is that dart hitting that person? And so what you do is you do, if this is 3D, you take the hypot of the, you know, x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared, and you square root that whole thing, and you see if it's within the radius of the sphere. And some people will just use that as their collision detection, right? Is the center point of the dart doesn't have any width, let's say, it's just a point. Is that point within the sphere? If it's within the sphere, congratulations, you hit them. And they'll do that sometimes actually to make projectiles better, right? Because this whole area over here doesn't look like it's part of the person, right? But if you shoot the dart at them and the dart just kind of passes past their shoulder, it'll hit because that's within the bounding sphere of the person. And it's really annoying when that happens, right? Like somebody shoots you over here and it hits you because the bounding sphere doesn't snap to your actual body. Have you guys ever seen that in a video game before where like there's issues with bounding boxes and bounding spheres and things like that? And it's frustrating, you know? I mean, it's useful. Like if you knew that the game system used a sphere for collision detection, you could just shoot people like over here. Like they're hiding behind a wall or something, you know? And you just shoot this and they die, you know? All the time in Halo 2. Yeah, it's like super annoying. And so a lot of times what they'll do is they will generate a convex hull so that you can do a more precise point computation, right? But you can wrap this whole thing in a bounding circle, right? Because we're going to be doing 2D, not 3D. And so what you can do is you can wrap the convex hull in a bounding circle or bounding sphere in 3D. And then if you want to see if a point is within this area, if it's outside of the circle, the answer is false, right? But if it's within the circle, then you do the more expensive computation. Are you guys with me on this? So this is a very common trick we use in video games, which is common case cheap, right? Rare case expensive and accurate. So the things that we do the most, we want to be very cheap. And so if you've just got bullets flying through the world and you're checking to see if that bullet is within all the bounding spheres in the world, you want that to take place really fast. The seeing if something's within a convex hull isn't too bad, but each one of these things is a cross product, right? And if you've got 50 lines defining your polygon, then that's 50 cross products you have to do. You don't want to do that on every hole in your game. You want to discard. Do you guys understand what I'm saying here? Like, if you had a bounding circle around every hole, that allows you, like, there's just all these bullets and there's all these polygons. The bounding circle allows you to just say, nope, they're not intersecting. Nope. All those guys are outside. All those guys are outside. All those guys are outside. Oh, wait, this one's within the radius. And so if, let's say, this point here is within the radius, now you get to do the more expensive, more accurate test. And you come in here and you're like, okay, that guy's to the right of me. Then you do this one. Nope, he's to the left of me. Reject. False. Okay? And so it's not even like it has to be an either-or situation. You can actually do both a bounding circle and a convex hull to have the speed and the accuracy at the same time, which is a really nice compromise. Okay? So McLaughlin, what we're going to do for our next assignment is I'm going to give you a set of points, and you're going to wrap a convex hull around it, and then I'm going to give you points, and you're going to tell me, is that point within the lava? You know, we might have some polygonal lava. Is it within the park? Is it within the water? And yeah. Is there a fast cross product the same way there's a fast inverse square root? Cross product is, 2 multiplies and a subtract. Like, that's pretty good. There's probably, like, some people do it using trig, but trig's slow, right? Like, you use a trig function for it. Probably. The way that I'm teaching you guys here with the brute force approach is not a good way of making convex hulls either. And I will show you guys the better way in just 1 second. You want black magic? Yeah, I'm sorry. Computational geometry is a giant field. Like, you can get your doctorate in it. And the answer is probably there's much faster ways of doing this, but I'm just teaching you what I know with my basic level of knowledge. And this is similar to how Unreal Engine does it, right? Like, if you have collision detection turned on objects, they'll oftentimes generate a collision sphere around it, so it'll very quickly tell, like, if you're far apart, it'll just very quickly say, like, nope, they're not intersecting. But if the two collision spheres are over each other, then it will do a more complex whole computation to see if there's overlap. And so, because you want to be able to eliminate the common cases very quickly. And so in Unreal Engine, you can turn off precise collision detection if you want, and just use the spheres and boxes. So, all right. So this is a good rule to follow. Anything you're doing a lot of, you want it to be as cheap as possible. And so good question, is there a cheaper cross product? I think the cross product's pretty good. Square root's a lot more expensive than you would think a lot of times. Okay, so let's do this. So here's your assignment. You're going to be given a set of XY points like this. Okay. And you have to wrap it in a convex hull. So how do you do it? Brute force is one way. I'm going to show you a better way, but let me just show you the brute force way first. So just, how many points do you have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Perfect. We have 10 points. So we've got point 1, point 2, right? And so what you can do is you can check point 1 and point 2. You can check point 1 and point 3, point 1 and point 4. So you can end up doing 10 times 10, or technically not 9. But it's basically an order n squared, right? Number of possible pairs. You try every pair of points to see if they're part of the convex hull. Are you guys with me so far? Well, yeah. So the brute force approach, which is not good, you basically just start. Let's just see. Let's call this guy point 1. Let's see point 2. So we're gonna try this line here, and then you go through every point and say, are they all to the right? Cross product, cross product, cross product, cross product, cross product, cross product. Oh wait, this guy's not to the right. Reject. And so you have n squared number of pairs of points, and then for each one of those pairs of points, you have to do n computations. So that would be an order n cubed algorithm, which is not particularly good. It's not particularly. I mean, it's not world ending, but we can do better, right? So you can do it this way for your assignment. And so, okay, we rejected that one. Let's try P1 and P3 now. So P1 was here, P3 is up here. We draw a line. And then how do you take the cross product? Well, you take that line and you take this line, right? And if the answer is negative, it's to the right. Yeah, cool. It's to the right. Okay, now let's try this one. It's to the right. Try that 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 one. Oh, we got a positive number, right? Because everything over here is going to be positive. So if you cross product this guy with this guy, then you get a positive number. Reject. And so P1, P2 is not on the convex hull. P1, P3 is not on the convex hull. All right, let's try P1 and P. And so you just do this for every pair, and for everybody that passes, like this guy, everything you cross product it with is going to be to the right. And so this one would be added to the convex hull. You guys understand that algorithm? Triply nested for loop. No more undos, huh? I hit OneNote's undo limit. Interesting. Okay. So that's one way of doing it. And so, if you draw a line from here to here, then everything's to the left, right? And so what you would need to do is flip it around, right? Or, you'll pick it up when you come back the other way. But if you want to optimize it, you can just look for everything being to the left, and then you just turn the thing around. And what you're going to end up with, your output, you're going to make a vector. You're going to make a vector of lines, basically, and angle. You make a vector of lines, and these lines are going to be they're going to be directional. You're actually creating a graph. If you guys have taken 26, this is going to be the output. So it's going to be, P3 to P7, P7 to P5. I'm just making up numbers here. P5 to P9, P9 to P2, P2 to P6, P6 to P0. And then, maybe these three guys are just not part of the answer. Okay. And then once you have that, what you're going to do is you are going to wrap them in a bounding circle. And that's really easy. All you do is you find the center point of the, that's what we did, remember? This last one. We find the centroid. Center point. You do that by just averaging all the x and y values together. Maybe there's a better way of doing that, because not all the points should be weighted the same way. You probably, yeah. What you need to do, the simpler way of doing it is just to take the distance of every point to every other point, and find the one that has the biggest distance. Right? It's like maybe this guy has the biggest distance of 8.1, and then you put the center point halfway to it, and you set the radius of the circle to be 4.05, and then you draw a circle like that. Okay. So whichever pair of points has the longest distance apart, you find the center point along there, make that the center. It doesn't actually have to be the centroid, because these things don't have to be accurate anyway. And then you just draw a circle of length 4.05 around the thing, and you're done. So your output is going to be a vector of lines that are the points, and then a circle. So this is what your code's going to output. And then after that, you're going to test. Is that point within? Is that point within? Is that point within? Is that point within? Yeah, you don't... Ooh, just dropped my tablet. You don't actually need to know graph theory for this. It's just, technically what we're generating here is a graph, which is points connected by lines. That's all it is. Points connected by lines. That's all a graph is. Hope this thing still works. Uh-oh. Uh-oh. There we go. We're back in business. All right. The graphs that were covered in 41. We did a little bit with graphs in 41. Yeah, it's points and lines, edges and vertices is what they're called. Okay, so that's your next homework assignment. Let's see, cross product. We've got a working cross product here. Let's see how much I can give you guys. So we don't need a point class because vec2 is a point, right? It's an x and y location, so we're good on that. We should probably have a line class or something like that. Struct line, and that will be just this is one of the line segments that we're going to output. So it's going to have a starting point and an ending point. Because these things are going to be directed, right? Because the direction matters. Because the things are going to go clockwise, and then everybody to the right of every line is in the thing. And this allows us to do really neat things. Like you can have really interesting. Oh, no, this tablet's upside down. Never mind. But you can have polygons. That you can see if you're inside it. I don't know. We'll start working on the terminal FPS, but I don't know where to start with building the renderer. Yeah, we'll do that together. Don't worry. We got 18 weeks in the semester, and I've been kind of toying with it, and it's gonna be fun. It's gonna be be really neat. But this kind of stuff where we're talking about holes here and things like that, that's kind of really important, because one of the most common things you do is see if one thing is inside of another thing. Are they touching? Is it inside of it? And yeah, so we need a line, we need a vec, and then we need a circle. All right, so struct circle. So circle has a origin, right? Center point, and it's got a float. We're using doubles, aren't we? Double for the radius. Okay. And if I call it radius, it's because I had Russian calc professors visiting from Moscow, somewhat appalled at American students' study behavior. Why are none of you reading this textbook? We don't read textbooks, dude. We just want to come to class and like learn the stuff. I don't want to read a textbook. Yeah. Harlan might have seen some of that in Kozasa Sensei's class. You got to prep. You got to prep for it. You got it. When she says read this before class, you need to read that before class. Then Kearney's comments for the dot product function are. What did I miss? What did I miss?
That's assuming I was correct about the cross product.
Dot product? Yeah, 1 means the two vectors are pointed the same way. 0 means they're at 90 degrees. -1 means... How is that wrong? What's wrong about that? By the way, the dot product and cross product I'm doing here are normalizing the vectors, and this is also not efficient, and we should be passing these things in by reference, etc., etc. Like, this is not optimized code. I'm just trying to convey meaning rather than...
yeah, he actually just misread the comments.
Okay.
Fine.
So, yeah, technically dot product will scale with the size of the vectors, but I don't want to use it for that purpose. I just want to know, is something pointed the same way as me? And then for cross product, I want to know, is it to the right of me or is it to the left of me? You know, that's what we're doing with this. The full versions of dot product and cross product include magnitude as well. And again, you wouldn't want to normalize your things every time, right? You would just ensure that these vectors are always normalized. Yeah. Okay, so we've got a point, we got a line, we got a circle. All right, pretty good. In fact, I could probably rename this point, but whatever. You can use this for more than just points. It could be used as a direction and magnitude as well. Okay. Okay. So let's see how much we can do right now before I turn it loose to you guys. So we got a circle class. Let's do this. Friend OStream ampersand operator double left arrow OStream ampersand outs vec2. We'll just call it by value. It's not optimized, but I don't care. V cout. It's called chevron hell sometimes. Chevron hell. There's the format library, FMT. What did you not like? Yeah. The FMT library allows you to not do chevron hell. It's closer to like the C printf function. It's now part of C++ 20, by the way. And I don't want to see out it. That's a mistake I always make. And so with this function, we can print a vec2 to the screen, and we can write it to a file, or we can write it to a string stream, things like that. We'll just make our life a little bit easier. And this one will be a line. And we will output start to maybe end. So that's going to print out like 1, 2 to 10, 20 or something like that. Did you not my hold on, start? Hold on, end. And then for circle, we will print out what do we want to print out? Cout, outs. And I'll put the start with radius. So with these things, we can print our things. It'll make life a little bit easier for us. Okay. And then we'll have the ability to input things. So for a ends into L dot start and into L dot end. And then for U, V, V dot X, V dot Y. So this will allow us to input something from the keyboard. The operator double right arrow allows us to read from the keyboard. That would be CN, and it'll read, oh, nope, that will not work. You need to be a reference, and honestly, you should be too, but whatever. Expected unqualified ID. Isn't the right supposed to be positive for cross product? I don't know. Right. Just depends on which one's first, I think. Yeah. Which one is the first one? Okay. So this will allow us to CN into a point, CN into a line, and then we need to CN into a circle. This is just all quality of life things. It'll just kind of make our life easier in the meantime. You need to be a reference as well. Circle by reference C. And we'll read into C dot radius and C dot, actually let's do the origin first, I guess. Origin and C dot radius. Okay. So circle C is equal to read, please enter a circle, point, center, then radius. Let's call this center. Okay, so that'll read a circle, and then let's just test to make sure these things worked right. So we're going to read a circle in, and then see out it out. So g++ linear.cc. Please enter circle. It's going to be at 3, 4 with a radius of 10. There we go. Cool. So we know our point, read in and write out works. We know our circle, read in and write out works. Let's just try the same with a line. What do we call it? Line L is equal to read, please enter a line, 2 points, and then we'll see it out. Remember, whenever you guys do development, always test your code, right? So I don't trust myself. 3, 4 is the first one, and 10, 20 is the second one. Nope. Oh, that was a circle. Sorry. Ouch. Try that again. Okay. 3, 4 with a radius of 10. Okay. Then we'll go from -10, -11.1 to +22.2, -999.999. And it rounded. You guys know? Okay. Yeah. So CN outs work right. CN outs work right. Yeah. And whether something's to the right or left just matters which one you do first, right? If you reverse the order of the vectors, then you'll get the opposite result. Okay, so your assignment will be to read in a bunch of points, and then output a convex hole around it, and then wrap a circle around that, and then do point tests. So people will enter a point, and you say whether or not that's within the polygon. All right. So we got 23 minutes left. You guys have any questions about that? This is actually hopefully it's interesting for you guys. It's maybe a little bit too mathy. I don't know. Circles. Yeah. It's kind of fun. Can you show the circle class again? Sure. It's very complicated. It's got a center point and a radius. And so one thing that I would do if I were you is create a bool within function that takes a point. Vec2. You know what? I'm going to do this using point equals vec2. I'm just going to alias point to the vec2. You guys see that? So now I can call it a point. All right. So rather than a vector2, I'm just going to call it a point because it conveys more semantic meaning to me, right? Because vector 2s aren't necessarily points. It's just two numbers. Right? Okay, good. Okay, so I want to make a bool within function that's going to take a const point by reference p, and I want to return true if the point is within me. Do you understand? I'm a circle. I don't look like it. I look like a person, but I'm a circle. And we're going to pass in a point, and I'm going to return true if the point passed in is within the circle's boundaries, and I will return false if it's not. You guys ready for this? Okay. Double distance is equal to high pot. Center.x minus point.x, center.y minus point.y. So this is going to compute the distance between the point passed in and the center point of the circle. x1 minus x2 squared plus y1 minus y2 squared. Pythagorean theorem, right? Pythagorean theorem. That's what hypot is. I don't know. I mean, it's the hypotenuse of a triangle. I just wish they'd called it Pythag or something like that. Okay, so this is the distance. And then if distance is less than or equal to radius, return true. Otherwise, return false. Right? So there we go. All right. So if the distance is less than radius, we're true, and we can melt that down even further. Return high pot being less than or equal to radius. There, it's a one-liner now. One-line function. Okay. We will need to replace the equals in that less than or equals to the near function. In this case, you don't need to do it because it's less than or equal to. And the less than is a solid disk, right? And so whether or not something is precisely on the border doesn't matter at this point. It's double equals that you have to care about. Double equals is what you care about. The only reason why I put the equals in there is because it seems like if it does happen to be exactly on the boundary of the circle, that would be within, in my estimation. If you don't think the boundary of the circle should be within, then don't put it there. It'll come up a vanishingly small number of times. You know, usually for small test cases where you make like a 3, 4, 5 triangle or something like you only need to worry if you use a double equals. Yeah, single, because it's like this. Imagine you've got a solid disk, like a circle, a solid circle, and you're asking whether or not the edge of the circle should be included within the circle, and the edge of the circle is infinitesimally small, right? And so whether or not you want to include that infinitesimally small edge of the circle within the circle is up to you. But it's not problematic. Like if I did this, you know, it would not have that infinitesimally small edge of the circle included within the circle. So it'd be infinitesimally smaller. But I think it makes sense to me. Like if it happens to land exactly, precisely on the edge, that it should be within the circle. It makes sense to me. Less than or equal to is fine. Greater than or equal to is fine. Double equals, no bueno. Not equals, no bueno. Okay? Less than's fine. So basically the rule of thumb is with floats and doubles, always make sure there's a less than going on or greater than. Don't ever expect you to get a precise match on these things. They round. Always have a less than or greater than. Okay, so let's see if this works. So we're inputting down here. We're inputting a circle, and let's read a line, I guess. So point P is equal to read. Please enter a point. And see out. Alpha C dot within P. Okay. So it'll print out true or false based on if that point is within the circle. So the circle is going to be at 10, 10 with a radius of 10. And then, so it's 10 to the east, 10 north with a radius of 10. And let's see if point 0, 0 is within the circle. The answer is false, because it's further than 10 away. Right? Whereas if we put in 10, 10 with a radius of 10, and we put in 5, 5, that's within the radius of the circle. Okay. Cyberpunk 1.1 just came out this second. Cool. Oh, for consoles and Stadia. Yeah. Funny. I hope they don't. My daughter doesn't want the game to be patched, by the way. Her favorite part of Cyberpunk is just watching for glitches. She'll come in, she's like, Daddy, have you seen any glitches? I'm like, girl, it's been like 5 minutes. Of course I have. You know, and I was driving down the street and it spawned some cars in, and of course it didn't spawn on empty space, and so one of the cars flung itself into the air. So I'm just driving. These people are just peacefully standing on the side of the street, and one of their cars just starts flying into the sky. I'm just driving. I look at my rear view. The car comes down, crashing down, explodes, killing all the innocent people there. And I'm like, yep, just another day in Night City, you know. She's like, I hope they don't fix that, Daddy. It's so much fun. So, or John Wick T-posing. You're doing the suicide mission. He's just standing there like this, T-posing, narrating to you while he's T-posing. It's like perfect. Yeah. He's a hologram. He can T-pose and narrate. That's not a bug. That's Keanu Reeves asserting dominance over Arasaka Corporation. Yeah. Okay, so let's test it a little bit more. If it's at 0, 0 with a radius of 0, let's see if we can cause a crash. No, all right, that handled. 0, 0 with a negative radius. 1, 1, false. Okay. So negative radiuses are handled. That's good. Negative 10, 10 with a radius of 100. And we're at 0.56, 556. Yeah. Yeah, it seems to work. All right. So that you typically, when you're working with games, you do this kind of stuff all the time. In the Quake engine, it's called point contents. The point contents function. Let's see if I can find it. Actually, I have the source code on here. Quake original. Quake 1 source. Prozac custom TF source. KK Quake World server, that doesn't have source in it. Where did I put the original source code? client. There we go. Server. Okay, so this is the original Quake server code. Pull it up in Visual Studio. And let's see if we can find where point contents is. One-way upgrade. Sure, I'm sure. Ooh, yeah, sure. I'm sure this isn't going to break everything. Alright. So, let's find in files. Find in files. See if we can find point contents. Point content contents. Find all. Let's see if we can find this. 37 matching files. Okay. So, content equals PM point contents point. So you see how they're using Quake was written in C, not C++. And so for points, they're just using a two-dimensional array. They're using a two-dimensional array of origin, of doubles or something. And then they have this point function here. And let's go to definition, go to declaration, let's go to the definition of it. Okay, so it's taking in a vector 3. Look, see, it's very similar to what I'm building here. Vector 2, vector 3, that kind of stuff. And so it's passing a 3D point. That's an if. Don't use putty. Putty is like 300K, dude. If you're having trouble downloading putty, like, I don't know, your internet's probably wrong. Okay, so what man page do you want? Man. Yeah. Okay, so let's look at their point contents, and this is actually kind of fun for me because I've looked at the server source code before, but it's always interesting to dig into, right? And so what do we got here? We got a float, we got a clip node, plane, a hole. Remember how we were just talking about convex holes? Hole is equal to p move phys_ints 0. 0 is probably the world model, points to holes element 0. Num is equal to hole points to first clipping node. I don't know what that means. Let's see, it's a hole t. What is a hole t? Go peek it to the definition. So the definition of it is, so for a hole, and if this is changed, it has to be changed in the assembly as well. See that, Moya? CSI 45 right there. So it's got a bunch of planes, right? So you know how I was talking about how you had these planes that were dividing the world in half? Yeah, so you've got an array of planes. First, last, the minimum, so if the minimum point on it and the maximum point on it. So it forms a bounding box. So it wraps this hole in a bounding box. This is a vector 3. This is the minimum x, y, and z value. That's the minimum x, y, and z value. That's the maximum x, y, and z value. Okay? And so it allows you to do a very quick computation to see, it's a rectangular prism, right? It's a 3D rectangle. And it allows you to very quickly see if a point is within the hole without having to go through every plane and going through every plane and doing the vector math to see if it's to the right. Okay, so that's what a hole is. Where were we? Okay, here. So it's grabbing the first hole, it's grabbing the first clip node out of it, which I don't know what that means. Let's see here. Clip nodes, planes. Okay. If num is less than, while num is greater than 0, if num is less than the first clip node or it's greater than the last clip node, so these are indices, I guess. Bad node number, okay. So it's going to have a range from like 0 to 5 or something. And, okay. Node is equal to whole points clip nodes plus num, so that's pulling, that is probably an array of indices, I'm guessing, without looking at it. Plane is equal to whole points planes, which is a array, probably. And yeah, so it's indexing into an array. So it's going to grab plane number out of it. If the type is less than 3, I don't know what that means either. Then plane type minus plane distance. Otherwise, it does a dot product. If the dot product is less than 0, num equals children points to children 1, else num is equal to node points to children 2. So this is called a binary space partition, I think, is what's happening here. So they have a plane dividing the world into two, and things that are on the right side of the plane are in the right child, and things that are in the left side of the plane is on the other side. So the dot product in this case being if it's in front or behind instead of left and right. You know what I mean? So it's like what we're doing with the cross product, except they're calling it in front or behind instead of to the right or to the left. It's just the same thing rotated 90 degrees. And so this is just going to grab the index of the subchild to the right or to the left, and then it's going to continue doing this until it returns a negative number, meaning you're at the end. And so, yeah, I wish you'd comment this better and say what exactly was being returned. It looks like I think when you get to like lava or something like that, like maybe it returns a negative number to indicate you're actually at the smallest area, and that it's open space or it's lava or water or solid is my guess. So yeah, so what they're doing is they're traversing a binary space partition, and they're the world's divided in half, just like we had with our holes there. You have a line, and it's either to the right or to the left. If it's to the right, it goes there, and if there's a further subdivision, it goes there. And it's a login search. The whole computation we have here is a order n search. They're doing it as a binary tree rather than as a linear thing like we're doing. Like I said, our approach isn't very good. And so in log n time, they can navigate through the entire world and find, is this point solid? Is this point lava? Is this point, whatever. So let's see where it is used here. Whole point contents. Okay. Point contents. Let's see, where are they using this? Okay. So what the upshot is you call this function, you pass in a point, and it tells you what's there. Is it water? What is water? Go to definition of water. Aha! Yes, they're negative numbers. Called it. You tell that from the source code, right? Because it terminates once it gets to a negative number. So all of the planes in the world are in a positive index of all the different slices of the world, all the divisions of the world. And so it stops when it gets to a negative number. So I knew that the contents had to be negative numbers. And so it'll return empty if it's open air. It'll return -2 if it's within a solid wall. It'll return -3 if that place is water, -4 if it's slime, -5 if it's lava, -6 if it's sky. So cool. Yeah, and you can deduce that just by looking at the source code. Okay, so if the content is water, water type equals content. Okay, water level is 1, and then what it's doing. So this is pretty cool. So Quake actually supports whether or not you're walking water knee deep in water, waist deep in water, or over your head in water. And so the physics engine actually handles those differently. If you're up to your knees, if you're up to your waist, or if you're over your head. And so what it's doing is that it checks the point contents at your feet, and then it checks the point contents, that's average. You see that? It's averaging your minimum value, your minimum height, and your maximum height. You see that? Minimum, maximum. You guys see that? Minimum, maximum. Every person in Quake has a bounding box, a 3D rectangle, and so it is averaging the minimum and the maximum to get the midpoint. That's your waist, and then they do it again up 22 units, 2.2 meters basically. Because Quake uses centimeters as its base units. So, 22. Whatever it is, tenths of a meter. Not centimeters, would it be decimeters? I don't know. But yeah, it's basically 2.2 meters up. So it's like if it's above your head, right? So I think the Quake Soldier is 2 meters tall, if I recall correctly. And so 2.2 would be a little bit above your head. And so if that's water, now you're underwater and you're going to drown. And so it actually sets on the player every frame. It checks if you're within water. It then checks if you're waist deep, head deep, whatever. And it sets water level on them. And so pretty cool. And so that's one example of how point contents are used. Point contents at my feet, point contents at my waist, point content in my head, and that the physics engine actually uses this number to see how much you slow down in water and if you have to breathe and things like that. Harlan, do you understand? Kind of cool, yeah. So this is essentially the function you're going to be writing for your next homework assignment. The units are silly, yeah. I don't know. The 90s were a different time, man. I think they picked this unit just because the numbers are kind of easy to work with. Like if you're dealing with meters, like 1 meter at a time is too big, and a centimeter is too small. And so I think they just picked decimeters as the unit. I think. I don't know. It's an integer, right? So you don't have to use a double for it. I don't know. Such is life. It's ready to update. No, we're not going to update it right now. Anyway, so yeah, so it's actually kind of fun looking at save changes. Sure, why not? It's actually fun looking at that kind of stuff because you can see the way they did it was better than the way we're going to do it, right? Every time we test to see if we're within a polygon, it's going to take order n operations, where n is the number of points within it, whereas they're able to do it in order log n time. So Harlan, I know you're asking about, are there faster ways of doing it? And the answer is yeah. And this was code written in like a weekend, 25 years ago, 26 years ago. John Carmack's a genius programmer. All right, so I will push this out to you guys. What you guys need to do, is this. What you need to do is this. One, read in a bunch of points and store them in a vector called point cloud. Okay. So that's going to be your input. And again, a hole allows you to simplify that down, right? It's actually really hard to see if a point is within a cloud of another points, right? Because how do you do that? You got all these points in a cloud. How do you know if a point's within that cloud? I don't know. It's tough. That's a tough one. What you do is you make a convex hole around it, and then you see if the point is within the hole. So you read a bunch of points and store them in a vector called point cloud. Create a convex hole around the point cloud. I haven't shown you the better way, have I? You can brute force it, I guess. You can brute force it by trying every pair of points and seeing if all points are to the right. Kind of like on the line or right. Make a vector of lines that make up the convex hole. It's part of that, I guess. It's part of step 2. Step 3, make a bounding circle around the convex hole by finding the 2 points in the how does the cloud store information? Yeah, cloud computing, right? Cloud computing goes down whenever it rains, right? Cell phones fall out of the sky when it rains. So you make a bounding circle around the convex hole. You find the 2 points in the hole with the longest distance between them. Set the average between them to be the center and the radius is half this distance. Then let the user test points and see if they are within the hole. So A, if it is outside, if it's outside the bounding sphere, return false. If it is inside the bounding sphere, then cross product the point with each line segment, with each line in the hole, and return true if the point is to the right of all of them. Okay. So that's your assignment. That's your assignment. Any questions about how to do this, Prado? Think you can do this? Walker? Wolf? What do you guys think? Why me? I don't know. I'm asking everybody. Yeah, sure. You know how to make a vector, and you know. So the hard part is going to be. I don't think there's really a hard part. This is going to be a that's going to be an order n cubed algorithm. So it's going to be a triply nested for loop. For every point, that's a line segment. For every point, if they're all to the right, then add that line segment to the answer. You can work with me again on it, Rosenberg. It's fine. So for every point, for every other point, you're going to try every possible line segment, and then if all the points are to the right, and you test if they're to the right by using cross product, right? If they're to the right, then add that line segment to the answer. You're going to do that for all of them, and then that's going to give you a convex hole. And then to see if something's within then you're going to make a bounding sphere around it, bounding circle around it. For every point within for every point within the hole, try the distance to every other point in the hole, and whichever one has the longest distance, the midpoint is going to be the center, and that's the radius. And then to test if something's within the hole, you first do a quick radius check. So thing that already exists that I gave to you, that'll tell you if it's within. And if it's within the bounding sphere, then you can do the more precise test where you see if it's within the polygon by cross-producting it a bunch of times. And so this will actually give you it's a 2D thing instead of a 3D thing, but you can see that, you know, like real code, you know, works that way. You can have a very complex shape, and you can tell if something's inside of it or not. You can have a waterfall and see if something's inside the waterfall. Okay. Can I breathe? Point content test. Okay. It's very, you know, it's a thing. And it's fun. Like I kind of dig computational geometry. I actually enjoy it. You know, it's kind of neat to me. And then you'll be able to use this for like clicking on things, right? So you can actually have a shape, and you can click on it in the screen with your mouse and see, is the mouse click within this shape? You know, click, and then it highlights, right? Yeah. All right. That's it for today. I will write this up into an assignment and give it to you guys. There shouldn't be any. You could graph this, I guess, but you don't have to. It's all just numbers. I might even make an input tester for it or something. It's always hard with an input tester with doubles, but should be doable. Should be doable. Okay. All right. Did you guys learn stuff today? Did you have fun? Is that informative, entertaining, and informative? Hopefully, at least a little bit you learned today. This is the kind of math that goes into actually being able to make a game. Like I said, this part of the semester, I'm just going to start off kind of heavy on the math and computational geometry side of things, because these are actually really useful tools. When you get comfortable with them, you use them even if you're doing blueprints, you know. Is that guy to my right or left? You know, like I talked about last time. Should I dodge to the right? Should I dodge to the left? You know, these are the tools, and by doing this, you'll become comfortable with the tools of the trade. I learned I didn't need to type everything you did because you're deploying it. I mean, I could delete my stuff, I guess, but it's probably good for you. It's probably good for you to get it into your brain, writing it down. All right, thanks, you guys. I'll see you later, and if you have any questions, just mail me. I'm around.